Okay, hi everyone. Thank you so much for having me. I'm really disappointed that I can't be there in person for the meeting. I hope everyone's having a really wonderful time. My name's Cromartie. I'm an Einstein postdoc fellow right now at Cornell, and I'm also part of the NanoGrav collaboration. And today I want to talk to you about how we can make extremely precise measurements of neutron star masses. I just said mass in my title. Obviously, we're talking about neutron star masses here. But with pulsar timing and especially in this new data set that NanoGrav is developing. So let's go ahead and get started. Really quickly, I'll tell you what I'm going to talk about. We all know the motivation, but we'll mention that briefly. Do a quick introduction to pulsar timing and NanoGrav as an experiment. This is not going to be new information for very many of you, but I do always like to reintroduce these kinds of things because it's not necessarily a topic you run across every single day. Then we're going to talk about comparing some binary parameters between the NanoGrav 15-year data set and the 12.5-year data set. Then we will go into some more information about advanced analysis that we're doing, as well as future plans. And just a quick disclaimer, this is all totally preliminary. I'm not going to be able to present sort of comprehensive mass measurements results in the way, I hope that I didn't misadvertise through the title of my talk, but we are going to talk about some preliminary results and some interesting things that we're seeing. So, preliminary. Okay, we all know why we're here, right? Neutron star equation of state, not extremely well constrained. And these equation of state are translatable into observables, right? And so we have this mass radius relationship. I set an alarm for 2 minutes before my talk, I'm sorry. Okay, so the, pulsar timing helps us get precise mass measurements for certain neutron stars, for certain millisecond pulsars. And so as we measure more and more massive pulsar masses, we can put a very simple constraint on the equation of state, right? We know that each equation of state sort of has to account for neutron stars as massive as the ones that we're seeing. And so it's really not a particularly complicated way of providing constraints, but it is quite helpful. And we also know that it's helpful because these mass constraints can be used by other efforts to constrain the equation of state. Notably, radio timing and NICER have been a really powerful sort of combo for really great measurements of neutron star masses and neutron star radii. And we saw several different results from this over the past few years, especially last year with JO740, this extremely massive neutron star. Okay, millisecond pulsars, these are a subclass of neutron star, very rapidly rotating, highly magnetized neutron stars. They beam radiation out of their magnetic axes as they spin. We sort of interpret this, or we see this as a pulsating signal, but pulsars don't pulse themselves. It's sort of like a lighthouse spinning around in space. We know that there's something like 10 kilometers, 1.4 solar masses, but obviously that is subject to a lot of variation. These millisecond pulsars are spun up by a binary stellar companion. They accrete a bunch of matter from the companion, spin up to these really mind-blowing speeds, rotational rates, and their rotation gets very steady as well. And so this stability is really what enables pulsar timing. We know of about 400 millisecond pulsars, something like that. Okay, so quickly, pulsar timing is this process of creating a model that accounts for every single rotation of a neutron star, or of a pulsar, obviously. So in this top panel of the top diagram, it would be easy if the pulse arrival times were just this very steady, unvarying thing that wasn't subject to kind of modification by a bunch of different astrophysical effects, right? That would be great in terms of creating our models, but we know that pulse times of arrival are affected by a lot of different things. Things like the interstellar medium, things like binary motion, thousands of things can affect when a pulsar pulse arrives. And so the process of creating these models that account for each rotation is sort of a complicated one. And eventually, you come up with a model that has really great predictive power going far into the future, and can help us very precisely constrain some of these parameters. And so I'm just showing this plot on the bottom because I'll show some residual plots later, but this is basically differences in the predicted and measured time of arrival. And you sort of expect that if your model's doing a good job, you're going to see this kind of nice unstructured scatter around 0. Okay, so there are many ways to constrain and measure neutron star masses. The one we're going to be talking about today is Shapiro delay. This is a really great way to make precise mass measurements using pulsar timing. So pulsar timing for binaries, this is going to give us a simple description of the binary orbit, things like the orbital period, the eccentricity of the orbit, things like that. And the binary parameters, sort of are necessary for creating a good model, but in a subset of systems, you can see post-Keplerian effects. And so in this case, Shapiro delay is what happens when the pulsar kind of goes behind. This is usually a white dwarf companion. It's traveling behind the white dwarf companion along our line of sight. The gravitational potential of the companion is going to slow down. It's going to cause a delay in the arrival time of the pulses, as you can see in this diagram. Hopefully that's sort of a helpful illustration. And what's really great about this is that, Shapiro delay, the post-Keplerian description, it can be parameterized in various ways. But we often talk about range and shape to describe Shapiro delay, range being dependent on the companion mass and shape being dependent on several of the orbital parameters as well as the total mass of the system. You can combine these measurements of range and shape with the mass function and get out independent measurements of the pulsar's mass as well as the companion's mass. And so this is a really fantastic way to get precise mass measurements for neutron stars. Pardon me. Okay. So this is how the Shapiro delay signal actually shows up in terms of the timing residuals. So you can see that at conjunction, where this dotted line is at orbital phase 0.25, the Shapiro delay signal is extremely strong. And you can also see here that it's very dependent on the inclination of the orbit. And so we can only measure Shapiro delay very well in a subset of systems that are very highly, that are very edge on, because that delay that's detectable in the timing is only very large for very edge on orbits. You can see here the difference between even 89.5 degrees, the dark blue line, and 85 degrees is very notable. And so in order to be able to really measure this well, you usually have to have a fairly edge-on system. Okay, so we know that Shapiro delay has resulted in some very interesting mass constraints. Notably on the right is the Demarest et al. 2010 result, sort of the first measurement of a 2-ish solar mass neutron star. This right off the bat was very helpful in constraining the equation of state. And this is actually a NANOGrav pulsar, so I'm going to talk about this on the next slide. But this source has been timed for a very long time and will continue to be timed for a very long time by the NANOGrav collaboration. And not necessarily just NANOGrav in terms of pulsar timing arrays, but I'm coming at this from the perspective of NANOGrav. So 0740 is another more recent example. I talked about these results last year. They were published a couple of years ago. The initial results, we found a very massive, a greater than 2 solar mass neutron star that has also been timed as part of NANOGrav. This is just showing the sort of the full Shapiro delay signal on the bottom panel. But it's still probably the most massive neutron star that we know of, but we're still working to kind of further constrain the mass. The work that was done to both improve our mass measurement using extended timing with the CHIME telescope that was led by Emmanuel Fonseca last year, those priors were then used for the really fantastic NICER analyses that resulted in some great radius constraints. And so this was a nice demonstration of sort of the powerful synergy you can have between radio timing and X-ray and X-ray studies as well. Okay, so NANOGrav, the idea is that we are a pulsar timing array experiment. It's the North American Nanohertz Observatory for Gravitational Waves. The idea is that we are at first looking for a stochastic gravitational wave background of very low frequency gravitational waves. Our sources are supermassive black hole binary mergers that are occurring all over the universe. In time, we're going to be able to detect continuous wave sources, so sort of these single mergers, and other interesting phenomena too, such as bursts with memory. These kind of permanent deformations in space-time are detectable through pulsar timing array experiments. This is going to help us understand sort of the last parsec problem, right? What happens at the end of these supermassive black hole mergers, merger rates, populations of supermassive black holes. So it's a very powerful sort of experiment. And it's also going to help us, there's some exotic, interesting gravitational wave signals. We can also sort of probe non-GR proposals, alternate polarizations for gravitational waves, things like that. So there's a lot that can be done. But the relevant thing here is basically that we get a lot of interesting secondary science. And that includes, our data sets are very rich. We time a lot of pulsars over long time spans. And so this lets us kind of get a good handle on the mass of many of our MSPs that are in binaries. And you can see the plot on the right is just showing that, in this very low frequency regime, our sources are different than what is of interest to Lisa and LIGO, and they're very complementary in the kind of big picture of gravitational wave detection. Okay, so the NANOGrav 12.5-year data set, it came out in two parts, what we called a narrowband data set and then a wideband data set. These were published at the beginning of last year. It included timing for 47 of our millisecond pulsars over not 12.5 years, more like 13 years. But the difference between these techniques is basically that in normal pulsar timing, you're using some kind of template to extract your TOAs, right? It's this one-dimensional thing, and you use that to extract TOAs across the entire band of interest. And so you can see on the left, sort of the top is a classic profile, right, that you use for extracting these TOAs. And then the bottom is what you would use for wideband timing. So wideband timing is basically using what we call a portrait. So this means that your profile varies in frequency space and is a better kind of descriptor of what the pulse actually looks like across the whole band. In traditional pulsar timing, you can see, we subband the data and we pull TOAs out at many different parts of that band and end up having a lot of TOAs. But wideband timing is this process that lets you extract a single TOA and a single measurement of DM. I'm not going to go into a ton of detail about this, but it is relevant because we are trying to use the wideband data in order to make these mass measurements. It's actually sort of necessary for especially the more advanced analyses. And the wideband data set reduced our data volume by more than 30 times for the 12.5-year data set. And so it really is relevant. It's going to become even more relevant as we move to sort of using this ultra wideband receiver that's coming on GPT soon. The Parkes pulsar timing array is already experiencing this with their ultra wideband system and trying to use these portraits that evolve in frequency in order to do their timing. Okay, so this is what the data actually look like. Don't worry about the details too much here. I chose 1713 because it has all these interesting changes in DM and pulse profile variation and all kinds of very complicated things going on with it. But the idea is just that we have, the 12.5-year data set represents a very large amount of pulsar timing data, and this is for 47 pulsars. This is only a single pulsar. And you can see, we do this dispersion measure modeling, we call it DMX. This is sort of a piecewise DM measurement model. Okay, so really quickly, it's exciting for NANOGrav right now because in the 12.5-year data set, that resulted in the measurement of a common red noise process in all of our pulsars, consistent with this spectrum that's predicted for supermassive binary black holes. We're not seeing spatial correlations yet in the way that would actually result in a claimed detection of gravitational waves, but we do feel like we're well on our way. And so in developing the 15-year data set, we think that things are going well in the development of the new data set, and we're looking forward to seeing the results. Other pulsar timing array experiments are seeing similar things as well for their gravitational wave search results, as well as the combined international pulsar timing array data set. Okay, so the 15-year data set for NANOGrav adds 21 millisecond pulsars. It represents this really big jump in sort of the size of the data set, adding a lot of pulsars. We add something like 3 years of data. Currently, the narrowband data set has been completed for the 15-year, and gravitational wave background analysis is underway. But the wideband data set has been causing some interesting, we've been seeing some interesting problems that we are still sort of working to address. So those issues are still under investigation. I don't think it's that interesting to talk about them. I will also mention this is relevant to the mass measurements because we are using a new pulsar timing package called PINT. This is instead of using the sort of tempo or tempo 2 based those two very classic pulsar timing software packages. Right now we are doing analyses using both just for comparison, and we will continue to kind of compare our PINT results with tempo results going forward for a little while at least. This pipeline that we've integrated PINT timing into is very cool. We've been working really hard on it within the timing working group. It's basically tracking the whole process of pulsar timing for NANOGrav, from creating time of arrival measurements to actually doing the pulsar timing and creating models for, right now we're timing more than 80 pulsars. And so this is sort of an onerous process to create those models. But it's really improving our ability to be transparent in kind of each step of the process, as well as accessibility for students who are interested in pulsar timing. And so for those of you who have an interest in this, it will be made public very soon, actually. And so, feel free to check it out. The 15-year data set also presents, or it includes very large array data for the first time. So this is higher frequency. And that lets us also have 0437, which is a target of interest for NICER as well. So that's a really fantastic addition to the data set. The next data set that we work on will include chime data, which we saw from the Fonseca et al. Result last year, that integrating that daily cadence data can have a really powerful can create powerful improvements or notable improvements in our ability to constrain certain parameters. So chime data will be in the next one. That's the plan. Okay, so right now, this is just a kind of comparison between various binary orbital parameters between the 12.5-year data set and 15-year data set. This is like a subset of the binaries. And again, not finalized by any means, but this just serves as sort of a consistency check to make sure that no parameters are changing in ways that are really unexpected. So for X or A1 measured in light seconds, we are seeing only a more than 3 sigma difference. The sigma difference is just the difference between the 15-year and 12-year over the error, the error in the 12.5-year data set. And so we're only seeing more than a 3 sigma change in one of these pulsars, but the model has changed a little bit. There are other parameters that have become significant between the 12.5-year and 15-year data sets with the added data. And we're also changing the way the profile evolution for the pulsars being modeled. And so this kind of a change isn't particularly startling. We did this for other binary parameters as well. The binary orbital period, we do see a large change for J1600 source, but a lot changed in the model. And so this is sort of just to make sure that for the sources where there is a big difference in certain orbital parameters, we kind of have a sense of why that might be the case. And so a lot changed in that pulsar's timing model between the 2 data sets. We also introduced red noise into the model for 1614. This created a slightly high sigma difference in the binary orbital period measurement. Okay, so we also do this for the companion mass, these Shapiro parameters, right? So companion mass and inclination angle. So this is that sigma difference plot, same thing as the last slide, but then this is the actual measurement. You can see that we have some improvements in measurement of companion mass for several of these sources. We only see one slightly more than 4 sigma difference for one source, the model for which changed a bit. And so nothing too startling here that we're seeing. Same goes for the sin I, so the orbital inclination. We are not seeing anything. It's the same source, right? Kind of makes sense. There's a slight change in the measured inclination angle, but nothing startling. So the consistency that we see is sort of reassuring. Okay, so these advanced techniques, which just means pulsar timing techniques that aren't just sort of least squares fitting. We have been working on, and this has been around for a while now, but Bayesian radio timing, which helps us in several different ways, including getting a better sort of grip on the measured posteriors for various parameters and nonlinear dependence of the model. It helps us put physical priors, physically motivated priors on certain parameters, and that's especially relevant for things like inclination angle and companion mass. And it also facilitates model comparison. So the Bayesian timing is implemented in this new PINT package as MCMC fitter, for those of you who are interested. And so we are working on integrating kind of a step in the pipeline for certain pulsars where we want to get this more complex modeling done as part of our normal timing scheme. So right now, there's also this Fonseca et al. 2016 style chi-squared gridding. So gridding over the inclination angle and companion mass for Shapiro delay parameters in order to get a better measurement of the pulsar mass. So the chi-squared gridding is also going to be incorporated into the pipeline. And so I mentioned the wideband data set because the wideband data set really makes, especially the kind of Bayesian pulsar timing possible. The data volume is sort of too large for many of our sources to make that feasible for normal kind of analysis. Okay, and so here are some selected gridding results. I will just mention, so again, preliminary. All of the 15-year pulsar masses that we have so far, we've kind of done the gridding for the vast majority of our binary sources. Everything looks consistent with 12.5-year results and sort of all previous published results. And so that's a very good thing. So nothing too surprising there. There are some interesting new results. This 1630 source the low end of its 2 sigma confidence interval is more than 2.1 solar masses. I would caution against getting super excited about this because it is really poorly constrained right now. But it's interesting. It's sort of like what we saw for 0740 at the very beginning when we were just able to sort of constrain the Shapiro delay parameters. And so we're going to keep an eye on this one for sure. But it's just an example of sort of a new measurement that's kind of interesting. There are also some new pulsars in the 15-year data set. Obviously, I had already mentioned there are 21 new sources. This is just an example of the ones, the companion mass measurements we have for a couple of them. You can see that our ability to constrain these parameters it varies from pulsar to pulsar quite a bit. So 1312 on the left has a fairly poor constraint, but this other new pulsar 1012 on the right has a fairly good constraint on the companion mass and inclination angle. There are many sources also that have significant improvements in the measurement of companion mass and inclination angle. One example is this 2017 source. The error bars have improved by a factor of more than 2. And so as we add more and more data to the data set, we're going to be able to better constrain its mass. But we're seeing these very tangible improvements already. Okay. So we know from many different studies, but notably the 0740 work a couple of years ago, that adding these targeted observations in the radio at conjunction and also in these Shapiro delay troughs in order to better constrain the full sort of extent of the Shapiro delay signal can be very helpful in our ability to constrain the mass. And so we have proposed, and there's actually a project ongoing for several of these NANOGrav pulsars for which we don't have great constraints. And so, for example, this 1125 source, we already did get some supplemental time, but it's not helping us kind of constrain the mass well enough. And so we have possibly some additional supplemental time for that source. This 1630 source is also part of the ongoing observing project to do the targeted observations, as well as several other sources that I list here, but I don't have the grids for. And so we are looking forward to basically incorporating those new targeted observations into the NANOGrav data set and seeing what kind of mass constraints we can make. Okay, and I'll just mention really quickly, this is a non-NANOGrav result. But as an update, I think I presented very preliminary mass measurements for this 1231 minus 1411 source, which is especially of interest to NICER. But we do have an okay constraint of the pulsar mass. You can see it down here. It's not super well constrained, unfortunately, but we do hope that it's going to be a helpful prior for the NICER modeling, and we've been communicating with the NICER folks about it. And so this is a sort of a nice example of the MC-based timing, MC-based timing that we are doing with Pint. Oh, and I just say here, not Fermi, because we did look at Fermi data and we're not able to get any kind of significant mass constraint from the Fermi data. Okay, so stuff on the horizon, the 15-year data set, as well as, so we're gonna have a single 15-year data set. This is gonna include wideband and narrowband data. That is gonna be published alongside the gravitational wave background search that uses those data, as well as a paper about sort of NANOGrav noise budget and astrophysics results. This is all gonna be released together, alongside other pulsar timing array results, which is really fantastic, in early 2023. That's not supposed to say fully binary analysis, it's supposed to say full binary analysis. So basically the results of what I've been talking about are going to be presented in full, either within the dataset paper or as a standalone paper that would be published very close to the same time. So do look forward to those results early next year. I'm sure we'll have kind of more concrete measurements much sooner than that, but that's when they should be officially published. We are going to be doing those combinations of the supplemental GBT observations with a 15-year data set. You know, we're also kind of working on this larger review of Shapiro delay mass measurements over time, just to sort of see how our Shapiro delay constraints change as we add more data, and see if there are any trends in you know, overestimating or underestimating masses. But we're not seeing anything that suggests that there are any issues, right? Everything is agreeing within the uncertainty. So, okay, and then we'll get the GBT ultra wideband receiver, which is going to make this wideband timing even more important. We're also working really hard on this kind of proposed DSA 2000 radio camera project. So NANOGrav has been very involved in that. Having an instrument like DSA 2000 could be really helpful for higher cadence observations. That you know, this is a very long-term thing, but we will be able to time, you know, like 200 pulsars at much higher cadence than what we have now, and that's going to be enormously helpful for constraining masses, especially because it has, you know, Arecibo class sensitivity in its currently proposed design. And continuing to collaborate with nicer folks, of course. This is just the ultra wideband feed. I wasn't sure what to put on the slide. Okay, and so I can just leave my summary. Basically look forward to the NANOGrav 15-year data set, what we've been seeing in terms of differences between the 12.5-year and 15-year data sets in terms of binary parameters are not particularly startling. Things seem to be sort of in line. And so we're excited to be able to present kind of more final solid results soon. So thank you, everyone.